get to the law of sines a bit. But when I was putting together the solution sheet for the last homework assignment, and I got to which section, the last section, 6.2 or 3, there were these problems. Find the values of the trig functions of theta from the information. I realized, well, you sort of do have enough information, I'll show you, but maybe not. 47 says the sine of theta equals minus 4/5, and then it says theta is in the fourth quadrant. So as far as finding the values of the trig functions, if we know the sine and the cosine, we're golden, right? We know the sine, the cosine, we know the tangent, we know the cotangent, secant and cosecant. So really, you just have to find the cosine of theta, given this information. So let's just take a look at the unit circle. And we know that theta is around here in the fourth quadrant. Of course, the gradient is still 1. And the sine is 4/5, or if you like, negative 4/5, because it's down here. The side of this triangle is 4/5. So this really comes down to finding the length of this side of the triangle, because that will be the cosine. And you can see it's going to be positive. So how would we do that? Well, Pythagorean theorem says that this side will be square root of 1 minus 4/5 squared. Okay, that's one way to look at it. That's the way you can have the information you need. The other way has to do with a piece of information I haven't given you yet. It's holding off until we started to work on identities. But I think I'm just going to throw it at you right now for the moment. We'll come back to it. I think most of you, any of you who've taken this class in the past are familiar with it. But the idea is this. We pick some angle theta, and we know that its coordinates are what? Cosine of theta, coordinates at this point, cosine theta, sine theta. Well, again, we have a right triangle here. This piece is the cosine of theta. This piece is the sine of theta. And we ask, what does the Pythagorean theorem tell us about the relationship between them? Well, Pythagorean theorem says c squared equals a squared plus b squared. In this particular triangle, you can see that c is the hypotenuse, that's 1 squared or 1. A squared, well, it doesn't matter what you pick, let's just say sine. A is the sine, so sine squared theta. And then b is the cosine, so cosine squared theta. This is a very fundamental identity for trigonometry, sometimes referred to as the Pythagorean identity. You can see how that would come about. It comes right out of the Pythagorean theorem. And if you had that information, when you look at this problem, you don't have to go through all of this. You can just immediately say, well, I want to know the cosine of theta. If I have the sine of theta, I know that 1 equals sine squared theta plus cosine squared theta. Sine of theta is minus 4/5, so 1 equals 4/5 squared plus cosine squared theta, and then I get the same thing I have over here. I keep forgetting the minus, but it doesn't really matter since we're squaring. So cosine of theta equals, and I'm just going to say plus or minus for the moment. When I find the square root, 1 minus 16 over 25, or 9/25, or square root of 9/25 would be 3/5. You're really good in math. You can kind of skip all this mess by realizing that if the hypotenuse is 5 and the side is 4 of a right triangle, here we have a 3, 4, 5 right triangle. Saves a little calculation. So the only question left is now, is this plus or minus 3/5 for the cosine? And that, they give you additional information. Theta is in the 4th quadrant, so you say, what's the deal with cosines in the 4th quadrant? They're positive, so we know it's just 3/5. So I wanted to go over that. If you've already done it, or if you didn't do it, that's fine. I recommend when you get your paper back, which hopefully will be Wednesday, you go over 47 to 49. Make sure you can do those. First thing I wanted to kind of clean up. Second, if you were here on Friday, this is a repeat. If you missed it, well, you're lucky. I'm going to repeat it. Something I think is really important to recognize. This is just a small little trick here. The question was, what is the inverse cosecant of x? I mean, we talked a little about the inverse sine, the inverse cosine, and the inverse tangent. Or if you like, the arc sine, arc cosine, arc tangent. If it's a special angle, we have some strategy for figuring out what the angle is. If we don't, we can use a calculator because we have a button. We have a button that tells us what the value is. But for cosecant, and for that matter, inverse cotangent and inverse secant, we don't have a button. And it's really tempting to think, well, okay, sine is, well, let me write that. Cosecant of theta is 1 over the sine of theta. So maybe the inverse cosecant will be 1 over the inverse sine, and that would be a tragic mistake if you kind of take that in and make that part of your knowledge base, since it's completely wrong. Let's see how you figure this out. It's very straightforward. It's very simple. Let's just start with the cosecant, the inverse cosecant, and we'll give it a name. We'll call it theta. Right? We don't really know how to deal with the inverse cosecant, but we can get rid of it. because this is an inverse function, we can apply the function, the cosecant, to both sides of this equation. We can say cosecant of inverse cosecant, that would be the cosecant of theta. And since we're taking a function on its inverse, of course we just are going to get x. All right. Now we're dealing with something we know what to do with. The cosecant, we know, is 1 over the sine of theta. We can solve for this. Sine of theta is just 1 over x. And now we can apply the inverse sign to this to find out what theta is. So the inverse sine of sine of theta on this side equals the inverse sine of 1 over x. Again, here we're applying an inverse function to a function, so we're just going to get theta back. Theta was our cosecant, our inverse cosecant of x. So we know right away this is the inverse sine of 1 over x. All right, so the inverse cosecant of x is not 1 over the inverse sine of x. It's the inverse sine of 1 over x. This is how we can find it out. Applying the same process, we would find that the inverse cotangent of x would be inverse tangent of 1 over x, and the inverse secant of x would be the inverse cosine of 1 over x. So, I mean, you know, if you need to, you can memorize these, but I think it's better to know where they come from. All right, let's try a problem or two. If I want to find the inverse cosecant of 3.5, well, what's that going to be? It's going to be the inverse sine of 1 over 3.5. Well, that's something we have a button for, right? A couple buttons. So again, checking that my mode is in degree mode, that'll do. Inverse sine, that's the second key on a TI. 1 divided by 3.5, get about 16.6 degrees. In a particular problem, you might have more information, like something might be, oh, this is in the 4th quadrant, or something like that, and you might have to say, well, wait a minute, the sine function, the inverse sine function only gives me certain values, right? You might have to adjust it. It might be negative 16.6, or it might be a complement of 16.6. Okay, let's just do one more problem. related to inverse functions, and then we'll move on. This is from the book. Nice simple problem. You have a triangle. It's a right triangle. Its hypotenuse is 50. Its leg opposite theta is 10. So how would I find theta? Sine of theta, thank you, is what? 10 over 50, or 1/5. Okay, that's a good start. What do we need to do next? Take the inverse. Inverse of sine of theta is theta. So we just have the inverse sine of 1/5. Again, I think you can see right away that's not going to be a special angle. So our only recourse is to use a calculator. This is more a notational kind of thing. If I said to you, give me the exact value of theta on a test. This isn't so much a math question as a, what the heck is the professor asking? I said, what's the exact value? Well, the calculator isn't going to give you the exact value. So this would have to be your response. It's the inverse sine of 1/5. That's an exact value. You can't write it out as a decimal. All right, are there any questions about the inverse functions before we go on?
You said that 16.6 degrees would give us some problem with like positives. So like, what did you mean by that?
Oh, okay, so I wanted the cosecant of inverse cosecant of 3.5. So where could the cosecant be 3.5? Well, that's really the same as saying, where can the sine be positive? Right? It could be positive in the first quadrant, right? Positive in the second quadrant, but not in the third, right? Or the fourth, because there it would be negative. So if I told you I want to know the inverse cosecant of an angle that's in the second quadrant, well, clearly 16.6, that's over here, would not be the right answer. Right? So I want an angle whose cosecant, well, this is a sine, but whose sine is over here. So the question is, if this is 16.6, what's that angle? Anybody want to tell me what that angle would be? Yeah.
Is it just 180 minus 16.6?
Yeah, it's a supplement, so it's 180 minus that. Does that make sense? Okay. All right. We're going to talk today about a very important theorem in trigonometry, one of a pair. The first one we're going to look at is the law of sines. You might guess the second theorem we're going to look at, probably Wednesday, is the law of cosines. This is a tool we use to to solve triangles, and I want to give you the big picture on this before we go into the law of sines. I know I've said this before. I don't think I've said it very clearly, but we have a set of triangle congruence theorems. Congruence theorems from geometry. You should be familiar with SSS, SAS, ASA, put in brackets here, AA, AAS, and then HL. I put this in brackets here because if I have two angles, then of course I have the third one. So really these two are the same. This is really like ASA question mark A. I've got all three angles. So what I want to do is try and make clear what this has to do with solving a triangle. Why a triangle that I have these three components of is suddenly solvable. It's just a very straightforward argument, right? If I have two triangles that have, say, side 1, side 2, side 3 equal, SSS tells me that these two are congruent. Well, that means any triangle that has these three sides is going to be congruent. That is, it's fixed. It can't be something else. It can't have different angles. Right? So, if I have three sides to a triangle, I have a specific triangle. It's fixed. And therefore, I can solve for the other components, at least in principle. This applies to these other theorems. So if I know three sides, or I know two sides and an included angle, I know two angles and an included side, but we've already kind of beat up HL. HL is for right triangles. We know how to solve right triangles, so I'm just going to put a circle around that. But to solve these other ones, we don't have the equipment yet, and that's where we're going. There's one other thing I want to put out here. Looking at the big picture, those of you who recall really well your geometry, you'll know that angle side. Yeah, that's not the way to write it, is it? All right, that's the way it is. Angle side. In other words, if I have some angle, unintended humor, I don't necessarily have the triangle congruence. It's possible to have two triangles that have two sides congruent, a third angle, and they are not congruent. For example, I can have something that looks like this, where I have an isosceles triangle here. So if I have this angle, this side, and something this length, there are two possible triangles. So it's not a triangle congruence, but you can see that, well, knowing this information, we don't have a single triangle, but we can narrow it down to two possible triangles. There are other possibilities. We could have an angle and a side, and it turns out that this is a right triangle, then you would only get one. And there's one other case that we'll look at, which is you could have an angle aside, and then you can't even make a triangle. We'll get to this later. All right. So, what is this mysterious law of sines that we're going to look at, and how is that going to help us? All right. Let's just take a look at a general looking triangle. I'm going to call its vertices A, B, and C. So you can think of this as the vertice, or you can think of it as the angle at that vertice. And the opposite sides across from these vertices I'm going to label with the same letter, but with lowercase. And I'm going to do something very, very respectable. I'm going to drop an altitude here. Which I'm going to break this triangle up into two right triangles. I'm going to give this point the letter D, and I'm going to call this altitude H for height.
Bless you.
Okay, so that's the setup. Now we're going to use some trigonometry here. We're going to note that at H over B is what? H over B, this is a hypotenuse, this is a leg of a right triangle. That's the sine of angle A. Similarly, H over A is what?
Sine of B.
Sine of B. Okay, I have two equations here. They have nothing in common except H. Let's eliminate the H. This becomes H equals B sine angle A. This becomes H equals A sine angle B. These are both H, so we can just say B sine angle A equals A sine angle B. And now we want to rearrange this a little. We're going to divide through by AB, and we'll get that the sine of angle A over the length of the opposite side A is equal to the sine of angle B over the length of the opposite side B. And then we're going to do a terrific hand wave. I'm going to say, you know, I picked this altitude from C, but I could just as well have picked it from A or from B, and I would have gotten the third piece. I would find that sine of angle C divided by the length of C is also equal to this ratio. This useful piece of information is called the law of sines. It's not just a good idea, it's the law. This is worth memorizing. If you want to call the derivation, that's fine. All right, so let's think of a problem we might want to solve. Let's look at an ASA problem. Looks like this. We have a triangle and we have two angles, 48 and 57. And we know the included side is 10. Well, if we know two angles, we know the third angle, right? So we just have to calculate 180 minus 48 plus 57. What's that? 90, 105, 180 minus 105 is 75 degrees. So the law of sines tells us that the sine of 75 degrees over 10, that's the same ratio as, let's say, the sine of 48 over, let's call this side x, and we'll call this y. That's also equal to the sine of 57 degrees over y. Well, I have two potential equations here I can use. The first one, sine of 75 degrees over 10 equals sine of 48 over x. I can rearrange this. This is just x equals 10 times the sine of 48 degrees over sine of 75 degrees. These were special angles. I could just use my knowledge of them, but sine of 48 divided by sine of 75. That gives me approximately 7.69. So this is 7.69. And I can go through the same operation. I can find y. This is great. I mean, all of a sudden, I was stuck dealing with right triangles. Now I can solve, this is just a general triangle. Right? If I know at least two of the angles and one of the sides, I can find all the parts of this triangle. All right, any questions about this? All right. I think we should try one of these with some angles that we know. I have a triangle where one angle is 30 degrees. And another angle is 45 degrees. And we'll say one of the sides is 5. So how do I go about solving this triangle? What would be my first step? Yes?
Find the sine of 30 degrees over 5 equals sine of 45 over variable.
Okay, sine of 30 degrees over 5 equals the sine of 45 degrees over, we'll call this x. Okay. You know, I've made a mistake at times. I do this trick in my head. I say, let's just solve for x here, and then I write something down, and it's been pointed out to me that not everybody knows what I'm doing. So let me just go at this a couple ways, right? One thing I could do is multiply both sides by 5 times x. And then on this side I can cancel the 5s, then on this side I can cancel the x's. So I have x sine of 30 equals sine of 45. 5 times sine of 45. And now I just divide by sine of 30. So I get sine of 5 sine of 45 over sine of 30. That's one way to think about it. Another way some of you might like is, just have to write it again. Sine 35 equals sine 45 over x. I could cross multiply, right? X times sine of 30 equals 5 times sine of 45. And then I just, again, divide by sine of 30. Just want to make that clear. That's what I'm doing when I just kind of jump to this. All right, we're not quite done here. What is the sine of 45 degrees? Exactly. Yeah, the sine of 45 degrees. Square root of 2 over 2, okay. And what about the sine of 30 degrees? 1/2, everyone? Well, if I'm dividing by a fraction, that's multiplying by its reciprocal, that's 2. So 5 times square root of 2 over 2 times 2 is just 5 square root of 2. Okay. I'm not quite done though. I still don't know this angle, and I still don't know this side. So how would I go about figuring those two out? Let's start with the angle.
Having 180 subtract.
How about someone in the third row? Oh, that would be
Subtract 180 by 75.
180 minus 45 plus 30, 75 is 105. Okay. 105. Okay, so we have our pick. We could go back to sine of 30 degrees over 5 equals sine of 105 degrees over, I guess we'll call this y, or y equals 5 sine of 105 degrees over sine of 30 degrees. Okay. Sine of 105 degrees. That's not in the first quadrant, is it? It's in the second quadrant. But whether the sign is in the first or the second, right, we get the same positive value, right? So what's the reference angle for 105? Okay. Question?
No, I was stretching.
Oh. Could you tell us how did you get 100 and how did you get 75?
Use 180 minus.
Right, it's the supplement, right? So we have sine of 30 degrees. Okay, what can we do with that? We don't have an exact value yet for sine of 75. We have one for 30, but we're kind of stuck right now. We have to use a calculator. A few days up the pike, we'll actually be able to come up with an exact value for sine of 75. Okay. Everyone think they can solve a ASA problem now? All right. I think the thing to look at now is that squirmy problem I mentioned a few minutes ago. It's funny, I remember for years in my, when I was teaching high school, teach this, we just really work hard to write it this way, because I knew I'd get no end of flack from my students if I wrote it the other way. But really, you know, we're starting with an angle, and we're looking at two sides. So let's take an example here. What if this is a 30-degree angle, and this side is 15, and this side is 10? Not drawn to scale here. Let's try and apply the law of sines here and see what happens. So we know that the sine of 30 degrees over 10 is going to be what? This angle here we'll call theta. It's going to be the sine of theta over 15. And let's solve for sine of theta. Sine of theta equals 15 over 10 times the sine of 30. But we decided we know what the sine of 30 is, right? 20 or 3/4. Okay. Let's just do the obvious thing. We'll take our calculator and let's find out what the inverse sine of 3/4 is. All right, that's 3 divided by 4. We get theta approximately 48.6 degrees. Okay, so now we have a triangle here. Looks pretty good. 30 degrees, 48.6, 1510, and let's see, 180 minus 30 plus 48, 78.6 is what? 1.4, is that right? I need another 1, don't I? No, I think I had it right the first time. Okay, and once again, now that I know this angle, 101.4, 101.4, using the law of sines, I can find this third side. So, what's missing here? Have any thoughts on this? I know SSA does not necessarily determine a triangle. We found a triangle, but there's something else going on here. Anyone see where this other solution creeps in? When I said the inverse sine of 3/4, okay, where is the sign positive? Well, it's positive here in the first quadrant. Where else is it positive? 2, right? So there's some other angle over here has the same sign. What's that angle? This is 48.6. What's this? We'll call it theta prime. What's that angle? The other angle whose sine is going to be 3/4. We just did a problem like this a minute ago. Yeah.
Do you get the reference angle?
Well, this is a reference angle. So I'm asking what's the other angle whose sine will be the same value? Yes.
131.4.
$131.4. Okay, that looks very mysterious. Where did that come from?
Subtract the 180. Or
Yeah.
48.6.
It's the supplement, right? In other words, supplementary angle will have the same sign. Oh. Well, what does that look like then? We've got 30 degrees. And what angle we were solving for this angle? I'm sorry, we were solving for this angle. So this angle is now 131.4. Oh. you have an obtuse angle here. Remember, this is 15, this is 10. Now this angle here is 131.4. So that's our second possibility, right? We can go on, we can find, if this is 30, this is 131, we can find this angle, which is not going to be 101 anymore. It's going to be 180 minus 131.4 plus 30. So that's 161.4. So now we're at what? 2.68. 1. Yeah. So this is 18.6. And again, now we can use the law of sines to find this third side. Okay, that's good. There are two more cases here that you want to watch out for. Let me change this problem slightly. Let's see what happens when we create kind of a bogus scenario here. What if this side of this is 5? Okay, let's just make believe we're a little naive. We're not sure what's going to happen here. So we know that the sine of 30 degrees over 5 is going to be the sine of this angle theta over 15, right? So again, sine of theta equals what? 15 sine of 30 degrees over 5. This is 3 times a half equals 3/2. So theta is just inverse sine of 3/2. Okay, good. We can find theta, right? Can we find theta? What's wrong with this? What's wrong with the inverse sine of 3/2? Anyone who has a calculator, please, if you're not sure right now, pick up your calculator, type in inverse sine 3 divided by 2. What do you get? Error. What kind of error? Domain error. Calculator's even going to tell you what's wrong. What's the domain of the inverse sine? I know I'm repeating myself here. Here's the sine function, right? What's the range of the sine function? What's the range of the sine function? No, that's its domain. Negative 1 to 1. The range of the sine function is going to be the domain of the inverse function, right? Remember, inverse functions and their functions, the domain and range switch places. So this is outside of the domain. Well, that's good, because this is an impossible triangle. If you took a ruler and tried to draw this, you'd find that this side of the triangle, it would never reach the third side. It's an impossible triangle. there's one more possibility here with SSA, right? So we've got two solutions, we've got no solution. What do you think the third possibility is? I'm running out of possibilities here. One solution, right? Well, what would that look like? I have to make up a really obvious example. So if this is 30 degrees, I make it look like 30 degrees. This is 15 and this is 7.5. Let's see what happens now, right? Sine of 30 degrees over 7.5 equals sine of theta over 15. So sine of theta equals 15 sine of 30 degrees over 7.5, or 2 times 1/2 equals 1. Okay, so what we want to find is the inverse sine of 1. What's the inverse sine of 1? You can use your calculator, but you shouldn't need your calculator. 90 degrees, all right. Now before we saw that if we have a solution, its supplement could also be a solution. What's the supplement of 90 degrees? 90 degrees, right. So there's just one, this is a right triangle, there's just one solution. The length of this second side is just long enough to come down and hit the third side. Okay, so when you're solving triangles, if you're given SSA, you have to keep your wits about you. Right? You could have one solution, you could have two solutions, you could have none. All right.